a little bit about radians. Okay, so the purpose of this is just to kind of go over the whole argument, the things that we've done over the last couple of days in class, because I really want to give you guys a chance to understand this pretty advanced topic. I mean, it's a topic with all honesty, I didn't understand to its fullest extent until pretty recently, and I want to give you guys a chance to understand it better than I did coming out of school, and maybe give you a chance to understand radians better than anybody in this building. So let's get to it. So the big question we're going to try to answer in this video is how can we describe an angle without using degrees? And why would we want to do so in advanced mathematics? Which is ultimately going to be a very weird thing because we have to put out of our mind something that we're very, very familiar to, which is the idea of a degree. Like if I said 90 degrees, that immediately is apparent to all of us how big of a space that takes up. But if I say something like pi over 2 radians, it may not be immediately apparent how big that space is. Ultimately, the reason we want to do something about the degree dilemma, the reason we still want to stop using degrees altogether is because where it comes from. It's a cultural thing that's based in a culture that no longer even exists. We went through the whole kind of history part in class, like the idea of this ancient Babylonian culture kind of semi-worshipping the number 60, or at least viewing it as a very kind of unique and beautiful number. And so if you consider like a degree being part of a circle, 360 degrees, you see that 60 immediately there. It's 1/360th of a circle, which means that the idea of a degree isn't built on anything other than the idea of 60. And so if you come from a place that doesn't use 60 as its base counting system, like us or any other culture that may interact with us, it's easy to see why we wouldn't want to use it. It's not based on 10. It's not based on something that we would innately guess. It's based on 60. And so that's ultimately why we want to get rid of it, is because it's just not a natural way to think about an angle. You have to be taught this way to think about an angle. It wasn't something that that would immediately come to mind. And so when you start asking yourself some really important questions, and do keep in mind this is a video, so feel free to like pause it any time if you want to catch up or if you want to take these notes with me. So we have to think about what a radian actually is, and so the idea of a radian is that it's based on something that is present in a circle. In this case, a radian actually is using the radius of a circle to measure an angle, because we can always get a radius of a circle. Any culture can find this for a circle if they understand the circle, although they may not call it a radius. We just happen to. And so the big idea here, and I'm going to try to draw it, is that if you take a circle, okay, and you identify its radius, and the radius, of course, is the distance from the center out to the edge of a circle, this radius can be used also to describe the circumference. One thing that you guys did for me almost immediately was to figure out, like, if I take this radius value and start wrapping it around a circle, how many of those radiuses fit. Now, ultimately, that was to tell you that the number of radiuses within a circle are constant. That's always about 6.28, which you guys later found out to be 2 pi radiuses that fit around a circle. In other words, like this r, okay, which is a radius length, although it's curved, is the same as this r, which is the actual radius, which means this r space in here is also technically a radius big. Now the misunderstanding may be like, I don't understand, like why are you using like this radius value to use different things? But again, it's just about a fraction of a circle. And so we can call this angle 1 radian big, because a radian is exactly that idea of how much space does a radius take up of the whole circle, which also describes the same fraction taken up in the middle. Um, and so it's just really no more than 1 radius of space, but taken as an angle instead of the circumference. And that's really the idea that we can record here. And so a radian, here we go. Okay, so a radian is 1 radius of space as an angle instead of part of the circumference. Okay, so if you recall, like the big activity, the thing I had you guys do was measure the radius and wrap them around the circle. It always took up 6.28 radiuses, which gives us confidence that it should be part of a measuring system. And so like this is doing anything differently than degree did. Well, no, the answer is no to that. So like consider this for a minute. Let's make this side the degree side. And let's consider a circle. So we have a circle here. If you think about like what 1 degree of space looks like, and this is a warm-up we kind of did together. So let's say this is like 1 degree of space. Well, that 1 degree of space can actually mean a lot of different things. That 1 degree of space could actually mean like this curve. That 1 degree of space could be like this part. That 1 degree of space could also mean like the entire like pi slice here. And ultimately, it also describes 1/360th of a circle. Right? We're going to do the same exact thing with radians. It's a very, very similar idea, but it's not based on 360 degrees. It's based on radiuses. Let me choose a different color here. And so, like, if you think about a radian, think about that same circle. We're going to go ahead and find this piece. Okay? And so this right here is 1 radian. That can also describe this piece here, which is why we're using a radius. It can also describe this space here, and honestly, if you want to be really technical, it could also describe the space here. And so a radian is nothing more than an idea. It's a fraction of the entire circle. It just doesn't have to be, it's just not in this case a fraction out of 360. It's 1/6.28 of a circle, or 1/2 pi of a circle. Now remember, the 2 pi thing comes from actually calculating the number of radiuses that would fit in a circle, but leaving an answer pi. And so if you consider this circle with radius r, the circumference is going to be 2 times r, because that's the diameter, times pi. Well, if you want to find the number of radiuses, which is also a radian, we'll take 2 pi r divided by r. The r's cancel, which means there are 2 pi. There are always 2 pi radians for a circle. In the same way that there are 360 degrees. Oops. That there are 360 degrees for a circle. Okay? And so these ideas are actually linked. It doesn't do anything differently. It just takes up more space, but also we're not fixing the game ahead of time. We're not making sure that they're going to be equal parts of 360. It's going to be based on the radius value of a circle, so of course you don't expect it to be nice. Okay, so what does a unit of a radian look like? Well, we saw that here. I mean, I've been drawing it up here a couple times. The idea of a unit is the smallest unit of counting. In other words, 1 radian of a circle. And so I've drawn it several times, but there's actually a way we can calculate it. And so we can start with this idea that roughly 6.28 radians take up a circle, in the same way that 360 degrees take up a circle. So if we want to know how much space 1 radian takes up, we can actually do this calculation. This equality can actually evolve itself into 2 different versions of a conversion factor, or a ratio. We can look at it as 6.28 radians as is to 360 degrees, or we can also think of 360 degrees takes up 6.28 radians. Okay, now I know it's not actually 6.28. I know it's actually 2 pi, but for our purposes, this is going to do well enough because we're going to estimate it. And so if I want to calculate how much 1 radian takes up in terms of degrees, because we can't ever get away fully from degrees because they're practical, especially in terms of like interacting and building stuff. If we want to know how many degrees it takes up, we can actually use one of these conversion factors. Now, in this particular case, we're going to use this one over here. The reason we're going to use that one over there is because it's written the same way as ours, radians over degrees. So we can look at 6.28 radians as to 360 degrees. Now we can just cross multiply and divide here, but what you're going to find out is that the x degrees takes up approximately 57.3. Oh, yeah. So the number of degrees in 1 radian is about 57.3 degrees, and so 1 radian is approximately 57.3 degrees. Which this should not be surprising because there's roughly 6.28 radians in a circle. 360 divided by 6 is about 60, but it's not perfect because it's 0.28. So it's going to be 57.3. And so in both these representations of 1 radian, that's what it's about. A sixth of a circle is about 57 degrees, which is important if we're going to figure out like what a radian is really all about. We have to start like relating it back to degrees because we're so familiar with that. And so we have two really important ideas. One, there's 360 degrees in a circle, which is about 6.28 or 2 pi radians. Pi is always going to be part of our calculation because we don't have perfect numbers, but we do have a circumference. And if you round pi, since it's a rational number, it'll make your numbers imprecise. And the other thing we can now know is that with 1 radian is about 57.3. And so if we want to know the rest, what we have to do is something called benchmarking. Now, benchmarking just means like what are common degrees that we deal with, and what are the radian equivalents for that? Like, how do I go back and forth in the way that makes a lot of sense? And if I do this activity really well, then I should be able to figure out how to convert, any radian measure to degrees or a degree measure to radians. And so let's get into the benchmarking part. So the way we're going to do this is just first to look at a circle. Because again, if we haven't kind of caught on to this, angle and a circle go hand in hand. Because by looking at a circle and rotating like a ray, we can figure out quite a few degree measurements very, very quickly. So let's go ahead and do that. And so this thing, which I'm going to call a terminal ray, the terminology is not important here. It's just the ray that rotates kind of like a clock that creates an angle. And so if I rotate all the way around and end up back at 360, I have our first benchmark. We have 360 degrees, which is 1 full rotation, which is the same as 2 pi radians, which is something that we knew before, because again, that calculation, if you calculate the circumference, is 2 pi r, divided by r is 2 pi, 1 full rotation. If we go half a rotation, which is another very common benchmark, so we rotate to say here, well, if the whole thing is 2 pi, half of it should be pi. And so we have another benchmark here at 180 degrees, which is the same thing as pi radians. I'm going to drop the RAD part because if you're dealing with pi and you're talking about angles, you can bet pretty well that you're talking about a radian defined angle instead of a degree defined angle. So we have one at pi. So let's do that again, but instead let's think about another way we can chop up the circle. And so I think we can probably chop it up into fourths. And so one down here, one up here, combined with the ones they already have. And so if I rotate to here, that's half of the top, or a quarter of the whole. Since the top is worth pi, this should be both 90 degrees, which is the same thing as pi over 2, or half of a pi. Because again, if the whole top is pi for 180, half of that should be pi over 2. So half a pi, 2 halves is a whole pi. And so this should be 1.5 pi down here for 270 degrees, or just 3 pi over 2. We like to keep radians in improper fractions. That's one of the reasons radians is actually a pretty cool measure, because you don't have to like have any sense of like what a degree is. You just have to know how to chop up a circle into equal parts. Again, another reason why it's actually a superior measurement. So we can chop them in quarters, which means we can also chop up an eighth. Okay. Now I'm not going to chop up the whole circle like this because it's going to get a little cumbersome. But if I look at the degree measurement to this blue ray, that should be 45 degrees. Well, that's half of a pi, and so that should be pi over 4. Because if half of the top is pi over 2, half of that is half of a half, hence pi over 4. There's a couple other ones that make some sense here. One would be 30 degrees because I can chop the top up into 6/30s, and which means this would be a sixth of the top, or pi over 6. And then another really common one, or one that should make some sense in our head at least, is going to be 60s, because I can fit 3 60s in the top, and so 60 degrees should be the same thing as pi over 3. And so what this creates for us are some nice truths. And so, let's see if I can match color here. And so it is true that 2 pi radians is equal to 360 degrees. It's true that pi over 6 radians is equal to 30 degrees. It's true that pi over 4 radians is equal to 45 degrees. That pi over 3 radians, because there are 360s on the top, is the same thing as 60 degrees. Pi over 2 radians is equal to 90 degrees. And let's see, pi radians is equal to 180 degrees. Now again, this should point to why radians are such a preferred measurement, especially in upper level mathematics. Look at the beautiful patterning we have here with our fractions. We have 2 pi, pi over 2, 2, pi over 3, pi over 4, pi over 6. Because you can actually view pi as like pi over 1. And so we have some really nice patterns. Now, the reason why this is important, the reason we want to have some equivalencies here is so we can go back and forth between the radians and degrees easily. We're going to do it actually in a very similar manner as we saw the unitization of the radian. And so we can kind of create this situation where I create ratios and I can solve them using proportional reasoning. And looks like I can do it pretty much with any of the things the benchmarks I made below. But there's probably a best choice. Like if I was going to write a ratio out of any of the things I have here on the right, for me personally, I would choose this guy, the last one, pi radians equal to 180 degrees. The reason I choose it is because if I'm ultimately going to make like some fractions and try to do some proportional reasoning, I want to choose a thing that doesn't have fractions. I think that honorable mention goes to 2 pi radians and 360, but if I can have a choice to do with 2 pi or pi, well, I'm going to choose pi instead, because it just makes more sense to try to lessen the number of numbers I have to deal with at any one given time. Which now brings us to our last question: how do you convert from radian measurement to degree and vice versa? Well, I think you saw the procedure, but now we're just going to do it with 180 degrees. And so let's run this a couple examples, but first let's record our conversion factor. Which is going to be pi is equal to, and I'm going to drop the radians again, 180 degrees. And that's going to give us two possible ratios to convert: pi over 180 or 180 over pi. And so just depending on like the problem we're presented with, we'll have to make those choices. Now you have some homework where you're going to have to do this back and forth really quickly and just to kind of practice it, but the procedure tends to be the same. So let's look at least one of each here. So let's look at our first example. Can we convert, say, 80 degrees to radians? Well, first we have to decide which conversion factor I'm going to use. So I have 80 degrees over an unknown number of radians. And so I have to bring in one of these two conversions to actually compare it to. Now, if you look, I have degrees over radians, so I'll probably choose the same over here, degrees over radians, because I know it's written in the same style. So I'm just going to copy and paste it and set it over here. Okay. So now I'm into my algebra steps, because I have degrees over radians, degrees over radians. So I'm going to go and cross this up. So I have 180 times x is the same thing as 80 over pi. Now I am going to calculate in terms of pi, which means I'm not going to do anything with it. I'm going to treat it like a variable. But to find the number of radians, I'll go ahead and divide by 180, which will leave me with x radians is the same as 80 pi over 180. Now, technically, this is a good answer because it's an improper fraction. It does have pi, which means I'm not rounding. But I think I'd probably do a little something with the fraction, so I have to do some like conversion work here. So the first thing I can do is divide both top and bottom by 10, which leaves me with 8 pi over 18. And then I can do some, it looks like they're both even, so let's go ahead and divide both by 2. So this would be, let's see, 4 pi over 9. And so if I want to know what 80 degrees is worth, that's the same thing as 4 pi over 9 radians. And so it's not really like a difficult conversion, but it's important to know where everything comes from. Like I could have taught you how to do this conversion really well in about 5 minutes, and I'm confident you guys could do it. But I want you to understand what the radian is. And again, it's this idea that is part of it's just a different way to measure this angle that uses a radius. And it leads to this wonderful idea that a whole circle is worth 2 pi radiuses, or 2 pi radians, which we can then use to convert back and forth to this using the pi equals 180, pi radians equals 180 degrees conversion. So let's see one kind of from the other side then. Let's just kind of drop it here. Let's say I have a measurement in radians and I want to convert it to degrees. And so the conversion in radians will probably be in terms of pi. And so let's say I have pi over 12 radians, and I want to know what it is in degrees. Well, the first thing I'm going to do is decide, again, which conversion factor, at least which version of the conversion factor I'm going to use. So I have something, pi over 12 radians over x degrees. I'm probably going to, looks like I'm going to use this guy right here. The reason I'll use it because it has radians over degrees as well. And so that'll be radians over degrees. Now the fact that I'm splitting up my fraction and having a complex one should not mess you up, because right away we're going to cross multiply. And so it looks like we're going to end up with x times pi. Oh, x times pi with one cross equals pi over 12 times 180 over 1. Okay, so let's do some simplifying first. So let's still have x over pi on this side. Looks like I have pi times 180 all over 12. Because I'm just multiplying the fraction straight across. And then let's go ahead and divide by pi, which same thing is multiplying by 1 over pi, of course. And so it looks like the x number in degrees is the same thing as this kind of mess. It's not too big of a mess though, because check this out. It looks like I have pi on top, pi on bottom, so those actually cancel. And so it looks like my answer is going to be the same as just 180 over 12. Now again, I could probably put this into a calculator, but let's take an attempt just to simplify it. They're both even, so let's cut it down by 2. And so that's equal to, what, 90? Yeah, 90 over 6. They're still both even, so let's cut it by 2 again. We have 45 by 3. 45 times 3 is actually exactly 15 degrees. And so it looks like pi over 12 is equal to 15 degrees. Okay? And so again, we just have to use our conversion factors. It creates some interesting fractional work there, but it's not something that you guys can't overcome. And so this is hopefully going to help you straighten out if you need some straightening out how to do these conversions. So we have this thing called degrees that comes from ancient Babylonian culture. No reason it should be here other than the reason that they just got conquered a lot and the idea spread over time and became the acceptable way to measure an angle. Although it doesn't really make any sense, it actually makes more sense in terms of universality, since our degrees are kind of culturally biased towards Babylonian culture, to use that a measurement in radiuses, like in this observation that there's always the same number of radiuses wrapped around a circle, leads us to this idea of radians. The idea of a radian is that the one radius, the radius here is same as the radius here, so it describes the angle, much in the same way a degree is. A degree describes the amount of space. A radian does too. It's just a different way to measure it. It looks weird. It feels weird because it's new to us. But it leads us to some really interesting ideas. One, that there are 360 degrees in a circle, and so are there 2 pi radians, which allows us to do some conversions. But if we look at better benchmarks, better equalities, we found that pi radians equal to 180 degrees is actually a more applicable one, and so that's the one we're going to use. And so it allows us to actually do some arithmetic work to do some conversions. The radians to degrees is a little bit arduous, but the more you do, the easier it's actually going to be. So please keep that in mind. All right, so last thing you're missing, and some people did have to put their notes away for the last test because of this. Please don't let that be you. Please make sure you're doing a summary. And guys, I'm going to start cracking down on how good the summaries are actually going to be. So the summary, from this point forward, I'm going to make sure it's actually written in the way that it should be. And so here's how to look at a summary. So the very first thing, make sure you reread your notes. So go back through, reread it, and what you're going to do is you're going to highlight or underline. 5 words or phrases you think are important. And they're going to be important to answering the essential question, which is what is a radian and why are we going to use it? So what you're going to do is use those 5 words or phrases to summarize your notes. Okay? In other words, I should see those 5 words or phrases in your summary. And if I don't, you're not going to be able to use them on the next test or quiz. Because frankly, some of the ones I've been reading so far have been quite embarrassing. And so, like, this is the actual template you're going to use. So you're going to reread your notes, you're going to highlight 5 words or phrases, and then you're going to summarize the notes, answering your essential question in your summary. If those things aren't present for every single one of your notes, you're no longer going to be eligible to use them for your next test or quiz. All right, so I'll read 4 set in class, and I'll tell you again. But if you're watching this, I have full confidence that you're going to do that. Please also keep in mind, although you have the option to like copy my notes verbatim, they're not useful unless they're in your own words. And so the best use of this is not so much as to copy down what I have, but to join the conversation in your head and write down in your own words what you're actually seeing. All right. So that's it for radians. You can expect a lot more videos like this along the way, especially for trigonometry, because it is a very complicated subject. So use this information the best you possibly can. Do your homework. Make sure you can use radians for next time we meet. All right. So that's been that. Thank you from Miss Mosier and Mr. Collins. We'll see you guys later.